All right. So let me start off by saying you will never need to explain how this machine works. Just like with the IR, I explained how the machine works so you understand what the data is telling you, but you don't actually need to explain the machine in the assessment at all. I just find it's helpful to know it so that way you understand what you're looking at on the data sheet. So what we're looking at today is something called mass spectrum. What we're doing with this piece of data, and I'll show you which one we're talking about. Sheets. Here we go. We are talking about the data that we're getting at the bottom over here. Okay? And where that data is coming from. So what happens when I have an organic molecule is I am going to take that organic molecule, which I like to represent by M, my molecule, and what I'm going to do is I'm going to hit it with some electrons. And the idea is, with this electron beam over here, I'm going to knock off one of my electrons in my organic molecule, and if I lose one of my electrons, what do I get? A positive ion now. So that's the whole process of what we're doing here. So I am trying to take my sample, I am hitting it with electrons, and then what I'm going to get is a charged molecule coming out of it. Charged molecules can respond to magnets. So that's why we want it to get charged. The other reason why we want it to get charged is because this recorder here can only read things that are charged particles. If it's not charged, it doesn't read it. So I need to do that as part of my process. Now, some things to remember about this molecule is that when it's charged, it's not very happy being charged, and it might be unstable, so it could break apart. So one of the things it can do is fragment into smaller pieces. If it does fragment, it will have one fragment that will carry the charge and one fragment that will not carry the charge, because there's only one electron that's been lost. Oops, sorry. There we go. So this is the full molecule. This is the charged fragment. And this is the uncharged fragment. Do you want me to show you an example and write a molecule?
Oh, you missed what's on above the secant again?
It's a dot. So the dot represents not charged. Do you guys want me to show you a molecule as an example? So let's say I have ethanol, like that. Cool. It gets hit with electrons, and it knocks one of my electrons off. So now I have a charged particle. It is not stable, so it breaks apart. And it can break apart in multiple different ways. One way it could break apart is that it loses its OH, and I have a CH3CH2 that's left over. And in this instance, the charge has been left with the CH3CH2, and the OH doesn't have the charge. It could also happen the other way around, because it's all random. Maybe my CH3CH2 isn't charged and my OH is charged. Soda. So that's an example of the molecule breaking apart. And it can break apart in lots of different ways. Can't see it? Want me to zoom in? Is that better? So that's one way it can break apart. Do you want to see another way it could break apart? Huh? It just randomly gets the charge. So this is the full molecule. This is a charged fragment. This is the uncharged fragment, if you guys are wondering. Can I break the molecule again?
No.
No. Can I show you another way that it can break? So another way it can break is, say, for example, it breaks over here, and I get a CH3, and let's say the CH3 has gotten the charge, and I get the CH2OH, and that doesn't get the charge. Or it could happen the other way around, where that break happens and the CH3 doesn't get the charge, and the CH2OH gets the charge. So there's lots of ways it can break, and there's lots of different fragments that can be made. So we're just looking at how the organic molecule breaks. And you can literally break it anywhere. Because these two things add up to that guy. All right, keep going. Okay. So what happens with that mixture of charged ions is it goes through a magnet, and the magnet helps sort things by size. So if the item is smaller, it's going to bend more. If the item is bigger, it's not going to bend as much. All right? And so that's going to bend differently, and then it's going to hit the detector. All right. We okay? Okay. Let me grab the sheet. All right. So it goes through this machine, and I get the recording of information. Remember, the recording of the information only gets the charged particles. So if it's not charged, I'm not going to see it. And basically, it looks to see, okay, have I been hit with that size? Yes or no? Yeah, maybe. And that's how I get this data. All right, can I move on to the next sheet? All right, so this is my mass spec data. So what you see here is all these different peaks. These are representative of different fragments and how frequent we have that fragment. So on the bottom here, M to Z, that's the mass to charge ratio. And then this here, relative intensity, is out of 100%. So basically the machine looks at all the different things hitting it, and they're asking it which is hitting me the most, and whatever is hitting me the most, everything else is in a reference to that one. So there's two things I need you to do for the achieved on this assessment. The first thing is to identify the tallest peak. So in this case, this guy over here at, let's see, 85, 86, 87, that is your base peak. Yeah. And what the base peak tells you, so I just need you to circle it and write base peak, and that's enough for an achieved. But so you guys are aware of what that refers to. It means that it's the most common fragment. Most common fragment. Yeah. The other peak that I want you to identify is the molecular ion. The molecular ion is the peak that is the furthest to the right. Now, in some cases, like this one here, the molecular ion is really, really tiny. And so I wouldn't expect you guys to find it on the mass spec, because it would be like stuff like this that you probably would think is just background noise. The other reason why I might give you the molecular ion peak is because the molecule itself is really large and it's not stable, and so it never reaches the detector. So in situations like that, I will give you something like this, and I will tell you the molecular ion mass peak is that. So what this tells me here is the molecular ion, and that is telling you the mass of the molecule. Which is really useful information because you can, if you know the molecular formula, you know the mass. Are we okay with that so far? All right. What else was I gonna say? So I might show you some of the other examples in that booklet, just so you can see what I mean by which one's the molecular ion. So here's question number 2. So see, this is question number 2 now. All right. In fact, I'll tell you how to get an achieved on this assessment, because I know Clyde needs to know this information because he's going to be heading off to the Philippines. So this is what you need for the achieve for the IR. For the mass spec, I need you to label one of the two things, either molecular ion or base peak. I suggest labeling both, so that way you have 2 chances to get that. So this one's really easy to find because it's the tallest one. That's my base peak. And then I'm looking for the molecular ion. That's the one most to the right. In this case, it is very large and obvious, so I haven't labeled it for you. So I circle that, and that's my molecular ion. Furthest to the right. So that tells me the biggest mass. This one is at 86, if you guys are wondering. That little tiny one is background noise. Yeah. So you have to be kind of careful, and that's why you have to use the other bits of data to help back you up as well. So if it's not obvious, I usually label it, or the other thing I do is I give you the molecular formula or empirical formula to help, like this one. Okay? So we can do a couple examples so you guys know what you're doing. All right, so that's what I need for the achieved for the mass spec. And the last thing I need for the achieved is the CMMR. All I need you to say is how many carbon environments there are. 1, 2, 3. 3 carbon environments. You just count. 1, 2. I'm just going through it because it's really easy. I'm not explaining the why. I'm just saying this is all you need to do for achieved. That's it. That's all I gotta do for the achieved. It's a big jump. It's like redox. The achieved is really easy, and then the next step is a lot, and then you might as well do the excellence because it's not that big of a step after that. That's the ridiculous thing about chemistry. Yeah? So the good news is you should all pass. All right? So that's all you need to do for the achieved. The IR is the hardest. Everything else is just find the biggest peak, find the one that's most to the right, count the number here. Hopefully you get it. All right, shall we take a little GimKit break? Yeah? Before I give you more.